Well, thanks for watching my moon video here. We're going to do a quick look at the Apollo 15 moon video, get a little data, and we're going to do some physics calculations, and we're going to do a little simulation. So, thanks again. Let's go.
Okay, we're looking at the Apollo 15 moon flag waving video, and there has been much debate about this video, what it truly shows. And I was looking at this, and I'll tell you, I personally didn't think much about the flag on the moon showing much of anything or proving anything. But as I was watching this video, it struck me that there is something in this video, in the physics of the flag movement, that can prove whether or not this flag is on the Earth or on the moon. And that something is the fact that the flag is displaying a physical property known as simple harmonic motion. It is displaying periodicity. And by just taking some simple measurements, we can actually calculate the acceleration of gravity where this flag is at. Now I know the acceleration of gravity for the Earth and the Moon, and I have already calculated what the periodicity of the flag should be for each. So let's go ahead and try this. And what we are going to do is count the number of periods for a given time. A period being the time it takes the flag to go over and back again to its starting point. So as astronaut Dave Scott goes by the flag here, he is going to create a Venturi effect, which will pull the flag towards him. And at this point we'll start the timer, and we will start to count the number of complete cycles that the flag moves back and forth again. That's a period. Okay, here he's getting ready to go. He'll pull the flag pulls towards him. Okay, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. So we can easily see here that we had 15 periods in almost exactly 30 seconds. So we have, each period is 2 seconds. So remember that that number, because I've done this a number of times and I always come up with 2 seconds, just about exactly. So now we're going to head over to Georgia State University, where Dr. Rod Nabe has set up a great website explaining the physics of periodic motion. And we're going to find everything we need there to examine the motion of this flag. Thank you. Okay, here we are at the Georgia State University website, and Dr. Rod Nave has set this site up, and it's just a great site for physics. And everything is like linked. We have all the different types of physics and linked. We're going to go to mechanics. And mechanics goes into a lot of different things here, but we want to go to velocity and acceleration, and part of that is periodic motion. Okay, and we want to go to pendulum. Okay, now here we are. The equation for a simple pendulum. The first man to derive this equation was Christian Huygens, and some of you may know he was famous for his theory that light was a wave. And he came out with this equation in the 1600s. So he's a very smart guy. He's kind of like Isaac Newton. It's all right, Isaac Newton. He was very smart. But then we have our equation. T is the periodicity of the pendulum. Now, the flag on the moon is like a pendulum. It's really not quite like this simple pendulum, but we're going to start off with this. Very simple. We have the periodicity here, the time of the period, and we have the length of the pendulum. In this case, it would be the part of the flag that hangs down would be a pendulum, and then we have g as the acceleration of gravity. So this is a very simple equation to. It's actually an approximation of the true situation, but. So what's the length of our pendulum? In meters, it would be about 0.9 meters. That's slightly less than 36 inches, 3 feet. And that would take into account a little bit of material that was used for the hem on top. So it was very close to the true length. Now, what's the acceleration of gravity? Let's work just the opposite. We already know that we got a period of 2 seconds, if you remember. The acceleration of gravity for the Earth is 9.8 meters per second per second. Okay, so let's calculate what would be the pendulum, the period of the flag, if it was an ideal pendulum situation, which it's not. It would be 1.90 seconds, very close to 2 seconds. And this is the Earth now. Remember, we're getting almost perfect Earth time. Okay, but like I told you, we don't really have an ideal pendulum here, a simple pendulum. Because the length of the flag, the density, the mass of the flag is not all at the point on the end. It's uniformly distributed along the length. So we need to go look at a physical pendulum now. We don't need this one. This is a pendulum where the mass is not evenly distributed. We can go to a rod pendulum. The rod pendulum, this would be like the flag on the moon, or on the Earth. The mass is evenly distributed along its length, part hanging down. You know, another interesting thing about these formulas, you'll notice that the mass, it doesn't really matter what the mass of the flag or the pendulum is. that pretty much cancels out. It can be very low mass or very high mass. You get the same periodic motion. However, there are some effects of friction that need to be taken into account as you get to low masses, which I'll talk about. So here's our equation for a rod pendulum, which is essentially what the flag is: uniform density along its length. 2 pi times the square root of 2 times the length over 3 times the acceleration of gravity. So let's plug in what we know. Pendulum length. Now this is in centimeters now, so it'd be 90 centimeters. And the acceleration of gravity, once again, for the Earth, 9.8. What would be what's our pendulum period going to be for when we take into account uniform density? Well, it's less. It was 1.9. Now we're down to about 1.6. Right, compared to a period of about 1.9 for a simple pendulum. So this pendulum would actually be 1.6 seconds, which is what it should be on the Earth. Now let's take a look on the Moon here. What's the acceleration of gravity on the Moon? 1.622. So what would it be on the Moon? Almost 4 seconds. For a simple pendulum, it'd be almost 5 seconds. So, we're only getting 2 seconds. The flag on the Moon in the Apollo 15 video is only showing us 2 seconds. So this is showing us that the flag is on the Earth, because this is quite a difference. Now there's a couple issues here to talk about. The question arises, well, why are we getting 2 seconds when it really should be on the Earth? Let's plug this back in again, acceleration of gravity for the Earth, 9.8, okay. For on the Earth, it should be about 1.6 seconds. Well, we're getting very close to a simple pendulum time, but it really should be 1.6. Well, the reason why it's a little bit more, what about 25% more than it should be, is because the material of the flag is very light, and the atmosphere has a dampening effect on its motion, so it slows it down a little, and that is the reason why it's 2 seconds. Now, I've done experiments with a bath towel hung over a curtain rod in the bathroom, and I get, I adjust the bath towel to about 3 feet, 35 inches, and I get about 2 seconds. And it should be 1.6. For a bath towel, would be the same thing, uniform density, mass. And I get 2 seconds. So I get 2 seconds for the bath towel, just as we show with the Moon flag. So here, the flag is on the Earth. There's really no other explanation for it. The flag is on the Earth. And we're going to move on here to see if I can find it here. Pendulum Lab. Okay, now we're at Pendulum Lab, and we are the University of Colorado. Let's set this up here. So we're at the University of Colorado. About, here we go. University of Colorado. Let's look at the credits here because this is a great program. Michael Dubson. Excellent little program here. Okay. So why am I here at the University of Colorado? Because let's plug in our length of our, we want to make it about 0.9 meter. Right, there we go, 0.9 meters. The mass really doesn't make much difference. It just doesn't. But you know, the mass of the flag is going to be low. Okay, friction. Well, on the Earth, we're going to have significant friction. We're on the Earth here now. This is already all built into this simulation. And let's look at what would the flag look like on the Earth. That would be the flag on the Earth. Let's get our little timer out here. There we go. Nice timer. And let's get a little motion going here and start the timer. See, 1.9, almost 2 seconds. Just what we're getting with the flag on the moon. This is a simple pendulum now, remember. About 1.9. It doesn't really vary much, even if you go 1.9. Okay. So the idea here is that we got 1.9 seconds. And it's kind of, what's nice about this is if you throw this around, you kind of see, and this is how the flag acts in all the videos on the moon. The flag acts like this. Pretty much how it would act, because this is Earth. This is Earth now. So I don't think anybody's really asked the question, how would the flag actually act on the moon? Well, here's the moon right here. It's a little bit less friction. Well, there's going to be less friction on the moon. Although there's enough, the bending and flexing of the material will slow the flag down. It doesn't go forever. It's going to slow down. So we can say probably something like this. And once again, a simple pendulum. What's this going to look like on the moon? Okay, the astronaut kind of whips the flag as he's trying to put it into the ground. I mean, does that look like what we see in those videos? This is what the flag, the moon flag, really should look like on the moon. Is this what we see? No, we don't see this. I mean, the flag should look like it's in slow motion on the moon, and it does not look like that. Now we start our timer here, you'll see that periodic motion is about 5 seconds per simple pendulum. Now we can approximate, let's take the midpoint, because the flag's mass would be uniform, so it really would be the midpoint here. So let's make this about 0.5. This would be probably more accurate for what the flag really would look like on the moon. We're on the moon now. But still, let's start our timer. It's going to be a little quicker. Yeah, it's about 4 seconds. Okay. It just doesn't look like that. It doesn't move like that on the moon. It's going to be almost 4 seconds. This is not quite according to our formula either. So let's look on like the Earth. Okay, here's what this would look like on the Earth. More of a physical pendulum. Of course, we got the friction too low for the Earth, so it's going to go forever. This is what it should look like on the Earth, and this is what it looks like if you watch the videos, the moon videos. The flag acts more like this than it acts like it should on the moon. It should look more like this. It should look more like that. Okay. So I think I'm building a case that the flag is definitely on the Earth. Well, thanks for watching, and we'll talk some more about this. Thanks.
Did you think the government would lie? There's more to a picture